Hello, my name's Adrian Harris. Welcome to the Micromaterials Applications Laboratory. We'd like to introduce you today to micro-impact testing. Before we launch ourselves into that technique, I just should introduce you to the instrument itself. I guess that a lot of people are going to be unfamiliar with the instrument. So this is a NanoTest Vantage instrument. It's a multifunctional instrument. It can perform nano indentation and micro indentation for measurement of hardness and elastic modulus of materials. It can perform scratch testing and wear testing. It can perform impact testing, which is what we will look at today, and also a multitude of other tribological techniques. The other thing we can do is we can actually perform these tests in different environments. So we're not restricted to just working under ambient conditions. We could actually submerge samples in liquids. We could test samples in controlled humidity environments. We can heat samples up, we can cool samples down, etc. So we can replicate a wide range of real-world engineering scenarios. The instrument itself is a two-load head instrument. It covers a very, very wide load range. So this is a low load head that goes from basically 0 up to 500 millinewtons of load, and this is a high load head. It takes us right through to 30 newtons. And both of these two loading heads actually can perform all of those measurement types that I've introduced and work across all of those environmental conditions as well. The other thing that's important on the instrument, of course, is the optical microscope. And so that allows us to identify and locate particular regions of interest on a sample, and then the sample stage system will automatically replace that sample from the microscope to whichever of the measurement heads we're using with submicron precision. Okay, we can then perform the test, return back to the microscope and investigate the test site. So, onto the sample that we're going to look at. This is the sample we're going to use today. It's a DLC, diamond-like carbon coating, on a steel substrate. I think it's about 4 microns thick, this one. So here we've just got one sample mounted up. It's a dedicated test piece. But we're not restricted to working with just one sample at a time. We can work with multiple samples simultaneously mounted, and they can be of differing dimensions. So clearly here what I've got is 3 coated metallic samples, and I've got a bulk ceramic sample here, which is 3 or 4 millimeters, about 4 millimeters thicker than the metal samples, and that's no problem for us. We can mount all of those samples simultaneously on the instrument, reference the desired test start point on each of the samples using the optical microscope, define the experiments, and then the system will automatically run the tests on those samples one after the other. Perform tests on the first one, then move to the next one, perform the test on that one, then on to the third one, etc. With no user intervention necessary. Let's put that one to one side. And then we have here just an example of some engineered components. So these are not dedicated test pieces. These are real automotive engineering components with quite a complex geometry and a particular location on them that needs to be tested. That's no problem. We can mount one or several of these as well and access exactly the region of interest. So it's a very flexible system in terms of what we can put on it. So back to our sample of interest, which is the DLC coating. Very, very simple to put that on the instrument. We just pop it onto the sample plate receiver like this, in front of the microscope, tighten up that screw, and basically we are now done with the hands-on side of the setup for these tests. We can now pretty much concentrate on what's happening on the computer screens. So if we come to the computer screens, we've got 2 windows of interest here. One of them is the main NanoTest software screen, which is a nice, intuitive, simple interface to use. And the other one is the microscope image screen, so we can actually see the surface of the sample here on the microscope screen. So this blue box here around this microscope position just tells us that currently our sample stage system is at the microscope. You can see there are various other measurement stations available on the instrument, depending on what the configuration of the instrument is. So this instrument, as we said, has both the low load and the high load heads. Today we're going to be using the high load head. Let's configure our test. So the first thing we want to do to configure our test is to identify a suitable test location. And so as I said, we've got the microscope image here of the sample surface, and we can actually manipulate the sample around in front of the microscope using the sample stage control screen here. And we can manually drive stages around, okay? We can move the sample towards and away from the indenter to achieve focus. Or we can just simply use the point and click system. So wherever we click, gets pulled to the crosshair, and we can select that point for measurement. So basically what I'm looking for now is a region which has got no obvious damage pre-existing at it for our test to take place. And this looks as good a place as any to me. So once we've selected the test position, we can click on quit, exit that sample stage screen. And now we're on straight away to defining the experiment. Okay, so we go to experiment, we go to impact, and we go to define new schedule. So let's go to our first menu here. We select the experiment type. There are a variety of different tests that come under the name impact. The one we're actually doing today is called multiple impulse. So multiple impulse test actually involves repetitively accelerating a sample probe at a sample surface, a test probe at a sample surface, and then pulling it away again. So we're going tap, 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 tap on the sample surface. You can understand why in the past we've actually referred to this as a woodpecker test. And what we're doing is we're continuously monitoring the depth of the probe as those repetitive impact events take place. So we can define various important elements of our test. And the most important elements, we won't go through everything in detail now, probably the most important element is the load that we're going to use. Now, we already know a little bit about this sample, and we know that 1,500 millinewtons, 1.5 newtons, actually should lead us to some quite nice failure events. Another important thing is how long we're in contact with the sample surface and how long the probe is out of contact with the sample surface. And we define that using this impulse control on and impulse control off period. So they're both set to 2 seconds. So what that means is that the probe will be released and be in contact with the sample for 2 seconds, and then the probe will be removed from the sample for 2 seconds. And that will take place repeatedly for the duration of the test, which we set here, total sampling time. So normally our tests are between 2 and 10 minutes, something like that. For this demonstration, we'll keep it to 180 seconds, so 3 minutes. And the final thing of significance, perhaps, is the acceleration distance. So we normally set that with micro-impact testing to 20 microns. You can set it to longer or shorter, depending on what you want to achieve. But typically, we use 20 microns. So basically, what will happen is the probe will be accelerated over a 20 micron distance with 1.5 newtons of accelerating force. So it hits the sample surface, will stay there for 2 seconds, will be withdrawn. Now that process will be repeated 45 times. That's a 4-second total cycle time and 180 seconds total sampling time. So actually 45 impact events there. If we wanted to, we can repeat that test multiple times. So we could say, maybe I want to do 3 repeats and I want to space those maybe 100 microns apart or something. But for the sake of the demonstration, we'll just stick with 1 repeat. Once we've defined the experiment, we simply give it a results file name, and we will just call this 1500 millinewtons times 1, okay? Click OK, and then this is an important thing here, we add it to the schedule queue. And what that means is that that one experiment that we've defined it can be run alone by itself, or it can be one experiment of multiple experiments that form what we call a schedule. So what we could do now, if we so wanted, if we had more than one sample mounted perhaps, we could go around this loop again, define the test that we want to perform on sample 2, go to this button here, define start position, move the sample, move the sample 2 in front of the microscope, choose the start position, and then simply select the results file name and add that to the queue. So what would happen then is sample 1 would run, and then when sample 1 is finished, the sample would automatically be swapped for sample 2, and the test would run on sample 2. But as I said, for the sake of demonstration, we're just doing one experiment or one sample. So we click on finished, and then we're ready to start the test. So at this point, all we have to do is go experiment, impact, and then run schedule. We have the option to delay the start time if we want to. There are sometimes reasons we might like to do that, but today we don't need to. We can just start right away. And so now what will happen is the sample will be automatically repositioned from where it currently is at the microscope to the appropriate test probe, and the test will commence. Okay, so the instrument is now just placing the indenter on the sample surface to take a reference of where the 0 point is, where the actual starting surface is of the sample. Now it's setting the requested load. So what it's doing is applying this 1.5 newtons of load that we specified. So the probes in contact are just ramping up to 1.5. Okay, and here we go. The impact tests begin. So impact 1, impact 2, there it is. Okay, and as you can see, with each subsequent impact, the probe is getting slightly deeper into the sample surface. So we're about 5.2 microns deep now. So 2 seconds in contact, 2 seconds out of contact. Okay, so depth continues to increase. Normally, a very, very abrupt failure would appear as a large increase, a large change in depth between one impact event and the next. So depending on how sudden the failure is, the scale of the difference in terms of depth between one impact event and the next will change. So this sample is kind of somewhere in between, a brittle and a more tough response. So there we've got a fairly significant increase in depth, and there we go. So this is the beginning of our impact failure. Okay, so there it goes. So what we tend to say is here's some events of initial plastic deformation. This we tend to refer to as our fatigue period. Okay, and here is the onset of the major fracture. Okay. So what we often tend to do with this technique is we configure multiple repeats at various different loads, and then we perform some statistical analysis on the resulting data in terms of the scale of the depth of the initial impact event, in terms of the depth of the final impact event, etc. And actually, I think in another part of today's session, some of that results analysis will be covered. So we've got about another 50 seconds to complete, and then what we will do is we will move the sample back to the optical microscope, and we'll be able to take a look at our impact test site and actually look at the fracture that the fracture event that's taken place. This technique is not really limited to use with just hard coatings on metals. You could work with even bulk materials. We've done some very successful work recently here with bulk tungsten carbides, for example, to study fatigue performance. Okay, so that's the end of the test. So what will happen now is we'll get an option in a moment to leave the sample where it is or return it to the microscope focal plane. Once it's back at the focal plane, we can go straight across to the microscope and we can take a look at the damaged site. So the sample is just returned to the initial position. Okay, so we just click on this button here, yes, to return to the focal plane. Okay, so then we can just acknowledge the test schedule is complete, and then we can move to the microscope by simply clicking on the microscope icon, and over it goes. And there it is. There's the impact site. The damage is what you might call unambiguous. Some really large, chipped, removed pieces of material all the way around that impact site. So that basically concludes the practical part of the demo of impact testing today. Hopefully we'll have another video for you soon, but in the meantime, thank you very much for your attention. Bye-bye.